Swayam Prabha. Digital India. Educated India.
Welcome to the lecture on model building in linear regression. In this lecture, we are going to be continuing with the same case study that we've used earlier, that is predicting price of pre-owned cars. Now we are going to predict price as a function of the other attributes that we have in the data. So let's see how to move further. So before we go ahead, we just need to read the data set that does not have any missing value at all. We have already gone through the steps and we found that there was one extra column that was generated, and this was column X, as you can see here from the column names. We have removed the column X and have updated cars underscore omit underscore data, and now we have 32,884 records and 10 columns. Let's load all the necessary packages here. The first package is car, which we need to compute VIF, and the next package is ggplot2 for all the plotting. We are setting a seed using the function set.seed, and the seed number that I am giving in here is 1234. The set.seed function basically sets a starting number that you can use to generate a sequence of random numbers. It ensures that you get the same result, that is, if you start with the same seed number and you run your program every time, you will get the same set of values every single time. So now we need to split the data into test and train. So 70% of the data goes into train and the remaining 30% goes into test. Now before we split the data, we basically need to generate the index that goes into train, and we need to generate the index that goes into the test set, right? Now to generate these indexes, we are going to use the function sample. Now from this sample function, so we need to sample out 70% of the row IDs from cars underscore omit underscore data, and this we need to map to the original data, and that becomes the train, right? So sample basically takes two set of parameters. The first parameter is the total number of rows that are available in the data, and the second parameter is how many samples do you want to sample from the total number of rows. So the total number of rows that we have is the total rows that you have from cars underscore omit underscore data, and this can be found out using the function nrow, right? And to sample out 70% of the row from this data frame, I am just giving 0.7 into the number of rows in cars underscore omit underscore data. Now this basically generates 70% of row IDs from cars underscore omit underscore data. Now these row IDs need to be mapped to the train and the test set. Now to map them to the train set, since these IDs are row IDs, you need to map them in the row position. So here you can see that from cars underscore omit underscore data, I have used the split index on the row position, right? And that becomes the train set. Similarly, to map them to the test set, I am just going to negate them. So this means that whatever ID is not there in split index, that will be used as the test set, right? So this is how you generate your train and your test set, and I am just going to find the dimension of these. You have 10 columns in both of this. The train set has 23,018 records and the test set has 9,866 records. So the first model is where we are going to regress price with power PS, kilometer and age. Here price is the dependent variable, power PS, kilometer and age are the independent variable. So to regress them, you need to use the function LM. LM stands for linear model, and I basically need to give the entire formula. So I use a tilde sign here, and before the tilde you have price, and after that you have your independent variables. So here price is the dependent variable, power PS, age and kilometer are the independent variables. I also need to mention the data as train because I am going to use the train to build the model, and the test set is going to be used to predict the model, right? Once I execute this function, my model is stored under model underscore lin1. So let's look at the summary now. So to interpret the summary, we need to give summary function and the model name. Now before you execute this, you just need to include the options function where you set the stipend parameter equal to 999. Now this function basically suppresses all the scientific notations, and that's the purpose of this. So once you execute the summary function, you will see a following output in your console. The first line of this output basically gives you the formula that you've used in your function. The second output is the 5-number summary of residuals. So residuals is nothing but the difference between the observed value and the predicted value. Here the observed value is the actual value of price that's available in the data. The predicted value of price is where you use the estimates, that is the slopes and the intercept, and you multiply them with the corresponding input parameter, that is power PS, kilometer and age, and then you arrive at a predicted value. So, the difference between the actual value that you see in price and the predicted value is called residual, and what you see here is a 5-number summary of the residuals. So, the next section is for coefficients. Coefficients are nothing but the slopes that you see. Now, intercept is also a coefficient, and the value is given under estimate for all these coefficients. One important point to note here is that whatever values that you see here, it's given as power PS, age and kilometer. So, these are the coefficient values for these variables. So, ideally they should be interpreted as coefficient of power PS is 73, coefficient of age is minus 249, and coefficient of kilometer is given as minus 1088, right. So, these are the values under estimate. Now, every estimate comes with a standard error, so that is given under the standard error, and estimate by the standard error is the t value. T value basically tells you that the coefficient value that you have got, is that value by chance, or is there a possibility of seeing such an extreme value, right. So, your t value should be very, very high, because we don't want these values to be just by chance, they should actually be seen in reality, right. Now, probability is nothing but the probability of seeing such a high t value. To basically conclude whether a variable is significant or not, you need to have a very, very high t value, or you need to have a very, very low probability value, and this is something we have already seen. And just beside the probability column, you will also see the significance stars. Now, 3 is the maximum stars that you can get. It basically compares to the significance level. The default level is 0.05, and that is 5% of significance. So, what we have here is that the intercept, the coefficients of power PS, age and kilometer are very, very significant. That is what this signifies, right. So, just beside the probability column, we have the significance code. The maximum number of stars that you get in the significance is 3, and this is for a significance level of 0.1%. Now, the default value of significance is 5%, that is 0.05, right. So, what this basically means is that when you are trying to assess your model as to whether it is good or not, we would like to know whether we need to retain some of the variables or drop some of the variables, right. In that case, we basically do a hypothesis testing and test whether the coefficient is equal to 0 or is it not equal to 0. Now, in such cases, you set the significance level. Now, what this basically means is that whenever you have 3 stars, these estimates are accepted even when the significance level is 0.1%, that is when the significance level is equal to 0.001. So, like I said, usually it is 5%, that is 0.05, but what this says is that even if you set your significance level to 0.1%, then even in that case the estimates will not be equal to 0. So, that is how you interpret the significance code. Now, just below that you have the residual standard error, the degrees of freedom, right. Your multiple R squared is 0.56 and your adjusted R square is also equal to 0.56, right. So, when you have a multiple linear regression, we look at the adjusted R square. So, the adjusted R square value is very, very less, and just below that you also see the F statistic and the corresponding p value. So, now let us just predict this model on the test set, and I am going to use the predict function to predict model underscore lin1 on the test set. So, to predict it on the test set, we just need to give all the independent variables, and we are just removing the column price here, and that is why we have given it as -1. You can see the length of the predicted records is 9866, right. Now, we need to calculate a metric called VIF. So, it measures the degree of collinearity in our data. So, to basically compute the VIF value, we need to load the package car, which we have already done, and you need to give the function VIF stand for variation inflation factor, and you need to give the model as an input to this. So, what this does is it measures the multicollinearity. So, the reason we do this is because we want to know whether the independent variables are they related to themselves or not, and in the case where they are really related to each other, we need to drop them. So, a VIF value of greater than 5 is basically considered as very high, and such variables are basically considered to be multicollinear. We do not need to keep both the variables which are correlated, but the point is that here is that you are trying to keep only one of the variable and then trying to reduce the redundancy in your data. So, here the variation inflation factor for power PS, age and kilometer, all of them are between 1 to 1.3. and these are not high, and hence we can conclude that these variables are not multicollinear. Now let's look at model evaluation. So RMSE is the metric that we use for model evaluation. It stands for root mean square error. So we have a small function here that's defined to calculate RMSE. So you need to pass your observed value of price and the predicted value of price, and then calculate the RMSE value. So the RMSE is basically defined as root of sigma 1 by n xi minus x hat the whole square, right? So this is RMSE test. Y bar is the mean of the test price. So the variable difference is the difference between the actual price and the mean, right? And the RMSE base is calculated thereafter. So RMSE base is basically using the mean of the data that you have. So what we really need to understand here is that when you calculate the base RMSE, I basically try, instead of having a y hat, there my y hat is the y bar, right? So the mean of price. So while computing the RMSE base, it also has the same formula as the regular RMSE that you do, but just for the fact that instead of y hat you have y bar, right? So that's how RMSE base is calculated. Once you calculate the RMSE of the model, you can just return the result, and when we call it, we can see that the base RMSE is 7974, whereas this RMSE that you get after you build this model is 5116, right? Now this is a huge drop compared to the base RMSE. My base RMSE is roughly around 8000, and from there we've come to 5000, correct? So this is the difference that you get when you basically build a model, instead of assuming that we can replace the predicted price as mean of the column. So now let's look at the regression diagnostics. To look at the regression diagnostics, you need to predict the model on the trained data itself. Again, we are just excluding the price column because that's dependent variable. Now the first way of understanding regression diagnostic is a residual plot. So what you see here is a residual plot. I have basically given the code here. Now the x-axis on the residual plot is the fitted value or the predicted values that you can get from your linear model, and the y-axis is the residual. So the input, which is x, has been obtained from the model itself. So you give model underscore lin1 dollar fitted values, and the y, which is the standardized residuals, that you can just get by using the function artStandard and the model name. Once you do this, I've just used the labs function for title, x label and y label. The value of the residual is actually going down with increase in fitted value. So ideally the residual plot should have all the points scattered randomly, right? There should be no pattern, but here we can see a pattern, and that's the reason we cannot really consider this model because of this pattern. Now to just further emphasize on this result, if you look at a QQ plot, the QQ plot basically plots the theoretical and the sample quantiles. Now you can just use the regular QQ norm function and use the artStandard function and just give the standardized residuals as input. Now here also you can see that usually the QQ plot should be a straight line, but here you can see a curve, and that itself is an indicative that this model might not be a good fit, right? So let's do one more thing. Now that we have figured out that the model that we've earlier built is not good, let's just plot the variable of price from the data cars underscore omit underscore data train and test. So we have two plots here. One is where you have just price and the other where you have log of price. And both the histograms, I'm just plotting them one below the other using the grid.arrange function from the library grid extra, right? So you can see here that this is the original distribution of price, but when I take log of price, the price is actually normally distributed, right? That's something that's very, very clear from here. And this is what we are looking forward to, and this is the kind of distribution that we want. We don't want a skewed distribution, we want a distribution that's symmetric, correct? So log of price is basically helping us in arriving at a normal distribution, which is why we are going to basically retain log price, and we are going to transform the existing price to log price, right? So the same trend is also obeyed for the trained data and the test data. That is clear from here. So what we are going to do is we are going to transform price to log price. Now originally if you look at the head of the data, so these are the first 6 records that you have. So you can see that this is the value of price. So I transform the price to log of price. Now this is natural logarithm, and now if you look at the head, the first few values, you can see that these are the transform values. Now similarly I do the same thing for test as well, and here you can see that the test price has also been transformed. Now let's build a linear regression model. We are going to follow the same step. Now instead of model 1, I'm just going to save it as model underscore lin 2, right? This is the second model. the price that you see here is basically log price. Now we made all the changes in the data itself, and that's the reason we are just denoting it as price, right. So coming back to summary, the same interpretation holds good, and here you can see that the R square and the adjusted R square has improved, and the adjusted R square is now equal to 0.62. Now this is a lot better compared to the earlier model that we built. So now let's predict this model on the test set. So once we predict it on the test set, let's look at the VIF value, and even here you have the VIF values between 1 and 1.3, right. So this itself is an indicative that the three variables power, PS, age and kilometer are not multicollinear. So now that we've looked at multicollinearity, let's revisit the regression diagnostics again, and here you can see that we are predicting the model again on the train set without the price, and we are going to basically build residual plot. Now the residual plot is a lot better compared to the earlier residual plot that we saw. The data is more or less centered around 0, and this shows us that building a model has helped us. Now here in the QQ plot, if you see, though it's not very straight, it's still a lot better compared to the earlier QQ plot that we built, right. So to summarize, in this lecture we saw how to build a linear model. We looked at how to interpret the summary of a linear model. We also looked at how to transform the dependent variable and what effect does a variable have before and after transformation, and we also looked at regression diagnostics. Thank you. Welcome to the lecture on model building using random forest regression. In this lecture, we are going to use a random forest to build a linear model. So the first steps are the same as the earlier case. We are going to read the data without any missing value, right, and we are going to remove the column X. Once we omit the column S, we are going to load all the necessary packages. We need the package random forest to build a random forest model. Now again, we are going to set the seed as 1, 2, 3, 4. Now we need to generate index that goes into the train and the test data. So this is again similar to the earlier data that we used for building linear regression. Again, we are going to get the index and map the index to the cars underscore omit underscore data to arrive at the train set. And just for the test, we are just going to negate this variable, and whatever is not there in the split index goes as the test set. Now that we've seen what effect does transformation have, we are going to transform the column price in the train and the test set, and we are going to build a random forest regression model. Now we are going to model log price as a function of power, PS, kilometer and age. So random forest is the function. Now that is a part of the random forest package. So my price is the dependent variable and my independent variables are power, PS, age and kilometer. So this is the formula that we are using. I am using the train data, and the number of trees that I want to build is 100, and the number of variables that we want to consider at every node is 3. Now once you build the model is saved as model underscore RF1, and then it is predicted on the test set. Again, we basically remove the price column that's already in the test data set to predict for the prices. Now once we predict it, we again need to compute the RMSE. So here the test and the predicted prices are transformed. So we basically put them back into the original scale by using the exponential function, and then we basically calculate the RMSE test and the base RMSE. Now the value turns out to be equal to 4021. That is what you get after you build the model, and the base RMSE is 7974, so it's roughly around 8000. So you can look at the difference between the base RMSE and the RMSE that you get after you build a random forest model. So the RMSE value is almost reduced by half, which is very, very good. So the next metric that we are going to consider is the R squared value, for which we need to predict the model on the train data itself without the price. And once you predict it, we are going to use it to calculate the R squared value. Now the R squared value is basically 1 minus SSE by SST, where SSE is your sum squared error and your SST is the total sum squared. To calculate SSE, we compute the difference in price between the trained data set and the predicted values, and then we can square them and sum them. So that is how SSE is calculated. Now for SST, we basically again take the price from the trained data set, but instead of using the predicted price, we use the mean of the price, right? And once you compute the difference, you basically square them and then you can sum them. So 1 minus SSE by SST is the R squared value, and for us that value turns out to be 0.9. So an R squared value is considered good if it lies between 0.9 to 1. So in our case it's 0.9, so which is considered pretty good. To summarize, in this lecture we saw how to build a linear model and how to build a random forest model and how to interpret the model. We took a look at regression diagnostics and how to assess a model based on that, and we also took a look at how to interpret the summary for a linear model. and we looked at how to calculate R squared value and RMSE value.